Good morning, ladies and gentlemen, or afternoon, depending on when you're logging in. Um, so today we're going to talk about diffraction. There's also going to be a little bit on polarization as well. What you'll be doing today is you'll be watching this hopefully very short video by me. Hopefully I don't get too long-winded here. You'll be watching a short video from me, but you'll also, on top of that, be watching a video from Mr. Dewey as well, going over a couple demos and explanations of equations, and I'll talk about the equation as well. So you'll go through the slides, complete the day 5 exit ticket. I'll upload the link for the video here, and then there will also be a video for Mr. Dewey as well. So this video for Mr. Dewey is about 15 minutes long, and he'll talk about diffraction and how diffraction deals with light, and he'll also do some demonstrations with that, and then he'll also talk about polarization as well, and he'll do some demos with polarization that are kind of cool. All right, so I would like you to go watch that now before you finish my video as well. So if you could go do that, that would be awesome, because that'll kind of build on my video, will kind of build on top of his. So after you watch that video, you should see kind of get a good feel of what diffraction in light is. When you shine a light through something that has a whole bunch of slits in it, you get kind of this pattern of kind of what we call order of light. So you have like the first brightest central order of light, and then you get, or sometimes it's called the zero order, and then you get first order on the next one, second order, third order, and they keep getting dimmer and dimmer and dimmer. A great common example of this in everyday life would be like if you're talking about, if any of you have blinds in your house, just those blinds that are horizontal that you can open and shut. If you see blinds, or if you see light coming through the blinds, and it kind of creates this, it doesn't quite create a sharp light where the shadow is. It kind of creates a blurred or faded light. That's kind of the light um, bending around those slits or the blinds. The difference with like a diffraction grating that we use, like Mr. Dewey did in his video, is those slits are so compact together that's where we really get those really defined order points. Okay, so this is kind of the example that Mr. Dewey used. This top picture would just be like if we had one slit, and then the bottom picture would be an example if we had multiple slits, and that's where it forms that zero order, first order, second order, because we get a whole bunch of overlapping and constructive interference at those points, therefore creating those really bright spots on the screen that we are shining the light onto. Okay. So Mr. Dewey went through and he talked about an equation that we can use for diffraction, and it is m lambda is equal to d times the sine of theta, or instead of sine of theta, you can use x over L. Okay, remember m is your order number. So if you're talking about, your first order, it's just between, you'd be talking about the distance between that central or zero order and the first order. All right. If you're talking about the second order, then you'd put a 2 in for m. If you're talking about the third order, you'd put a 3 in for m, and so on and so forth. Wavelength, we know, should be measured in meters. Distance between slits, that's the distance between the slits on the diffraction grating itself. So we're talking super, like if you're talking a diffraction grating, you're talking super tiny numbers. Those are usually going to be in scientific notation. It'll be times 10 to the negative 6th or 7th or whatever it might be. The angle between the first and central and first order, that's actually a typo. It should be the angle between the central and whichever order you're talking about. It's not necessarily just the first order. It could be the second order or third order or fourth order, and so on and so forth. So kind of ignore that part right there. That's, like I said, that should be, I don't want to keep going that far. Like I said, that should be whichever order it is you're talking about. And then the distance, if you're using the other equation, if you're not given the angle, which most of the time you're not, because you're not going to be able to measure that super, super tiny angle, you're going to use x over L. And if you watch, hopefully, like I said, you watched the video from Mr. Dewey, he explained how if you take and plug in sine and tangent of a super small angle, for instance, if I do sine of 1, I get 0.017454, whatever. Whereas then I do tangent of 1, I still get 0.01745, and it's not until the 6th or 7th digit that we actually end up getting a different number. So we're talking hundredth of thousandth spot in our decimal. So when we're dealing with really small angles, we can just use sine of that. We can substitute in for tangent. So the x over L, we use x where x is the distance between each of my orders. So if I'm using first order, I would just use that distance between central order and my first order. And then the distance from this grading to the screen would be L. All of these need to be measured in meters. As always in physics, we always want to make sure that we are in meters. Okay. And if it doesn't ever give you, if a problem doesn't ever give you which order it is in, like if it doesn't specifically say first, second, third, fourth order, we're just going to assume that we are in the first order, because then it makes m equal to 1, and then essentially we can just not even worry about it. So here's an example problem. A reflection from a CD is seen on a wall. So this would be another common example. Would be a CD. If CDs are relevant anymore, I don't know if you guys even own CDs. We're kind of in the digital age now, so I don't know how many of you actually own CDs. But if the slits on the CD are 16 times 10 to the negative 6th, and to be honest, that's poor scientific notation. That should be, I guess that should be 1.6 instead, but that's okay. 16 times 10 to the negative 6 meters apart, and is viewed at an angle of 2 degrees. What is the wavelength of this light? So for this particular problem, we can just use the equation, the standard equation, m lambda is equal to d sine of theta. Okay, well, m is just going to be 1, so I'm not even going to worry about that. Wavelength is what we're trying to solve for. M would just be 1. I'm not even going to put it in there. Is equal to d. Remember, d is our distance between the slits, and that we're talking about the slits on the CD. So I would have 16 times 10 to the negative 6th meters. And we're going to multiply that by sine theta. Simple enough. Go ahead and solve for that. Hopefully you end up getting an answer of 5.58. I'm running out of room, times 10 to the negative 7th meters. Okay. And if you were to look that up, that would actually end up being green light. Okay. That wavelength would actually be green light. If any of you ever take a CD and reflect it onto a wall, you might see that it forms kind of a rainbowish color onto the wall, or it can. So that would be green light. Now, if you use this same light with a different CD, all right, and the wall is 80 centimeters away from the CD and the distance between the bands is 30 centimeters, what is the distance between the slits on the new CD? Okay, once again, we'll just assume that we're in first order. So we're still going to assume that m is equal to 1. But now the only difference is we're not going to be able to use sine of theta because we're not given an angle. And this is usually going to be the case because you're not going to be able to measure that super, super tiny angle. So what we'll do is we will say that my wavelength is equal to d times sine of, and now we're going to use x over L. Okay, well, we are We're still going to be using that same wavelength because we're still using same light with a different CD. So we're still going to use 5.58 times 10 to the negative 7th. Remember, that's in meters, is equal to D is actually what we're going to be solving for, because we're trying to figure out what is the distance between those slits on the new CD. Okay, and then we're going to multiply that by sine of, and it's going to be sine of x over L. Well, now let's think of what are x, or what is what x and what is L. Well, x is going to be the distance between the bands. I just realized there's a typo here. What is the distance between the band? I just meant bands. The distance between the bands is 30 centimeters. So we want that in meters. So that's actually going to be 0.3 meters. So we'll have the distance between the bands on the wall itself are 0.3 meters. Okay, but since we're assuming first order, we'll use 0.3. Now, if, for example, it was asking about the second order, well, then you'd have to put a 2 out front here, and then you would actually use 0.6 instead. Okay, but in this given situation, we're just using the first order, so we use 0.3. Okay, and then L is going to be the distance from that between your grating, or in this case the CD, and the screen, or in this case the wall. So that's going to be not 80 centimeters, but 0.8 meters. Okay, so you can find sine of 0.3 over 0.8, and then you can divide over. So we'll go ahead and solve for that real quick. So you should end up getting an answer of 8.53 times 10 to the negative 5th meters. That is how far apart the tiny little slits on the CD, that's how far apart they are from each other. Okay, so hopefully that makes sense. If you have any questions, please let me know. Your homework for the day is to complete the day 5 exit ticket in Google. Like I said, if you have any questions, please make sure you let me know. Have a great day.